Okay, everybody, this is Professor Ma, and this is the lectures on sequences. Okay. In particular, we're going to talk about three topics: the sequence notation of sequence notation, and the summation notations, and we're going to do one calculation formula for arithmetic formula, linear. What's a sequence? A sequence is a list of numbers, but it has to be in orders. And the first things you can think of is Excel. And here's a list of numbers: 2, 4, 6, 8, 10. They are stored in particular entry. In this case, the first F1 is the first entry. F2 refers to the second entry, and so on. So here's entry F1, entry F2, entry F3. Okay, but then the numbers stored in them, 2, 4, 6, 8, constitute the sequence. Okay, in other words, if I were to switch the 4s and 2s around in the first two entries, that would be a different sequence, just because I swap. We can write in this case, actually use the numbers of entries. Actually, we call that the index, and the entry, and use that as to write the formulas for the actual numbers stored. So, for instance, for even number, then in the 10th entry is number 20. In the nth entries, so n will be somewhere down here, nth entries, okay, and then you say what's the number in here? Well, it's going to be twice of n, okay, according to these patterns. Okay. Okay, and sometimes the formula has pattern we can recognize, and this is the sequence of R numbers. We can recognize patterns. Here's a sequence of square number. If you look at it for a second. Okay. And here's a sequence that for us there's no pattern, but for some other intelligent being, maybe, oh, I know what this is exactly. So what's a pattern? It is the underlying question, actually. Okay. Here's a definition of a sequence of mathematics. It's a list of numbers that output with the domain, we plug in 1, 2, 3, 4, meaning room number 1, room number 2. Then F sub n, we write as the actual entry, the actual numbers, 2, 4, 6, 8. Okay. So in this particular case, F, we call this 100 down here, we say as sub 100, because below sub. So this F sub 100, it means it's the 100 numbers on the list. And we can use variables. Say this is a Joe Blow. This is a generic entry in the sequence. The nth numbers down the list. Okay. Why do we say that? Well, because I can talk by its neighbor. Fn minus 1 will be the number comes before it. M plus 1, F sub m plus 1. And likewise, m plus 1 will be the number after Fn, okay, in reference to this Fn. Okay. So the sequence of square number, the third number is 9, fourth number is 16, fifth number is 25, and if you think about it, Fn is n squared. For even number, Fn is 2n. For R number, you take the even numbers, you subtract 1, you get R number. Sometimes add 1 to get, depending on where the R number starts, so you can either, 2n minus 1 or 2n plus 1, you get all the numbers start from 3 R number. So, say, what did you say? Say, if I'm talking about 2n plus 1, then this will be a sequence of 3, 5, 7, 9, okay, starting with these. Okay. And if I want the sequence to swap signs, alternate sign, plus minus, then a lot of them shows up like that in the features. And what we do is multiply this factor, -1 to the nth power, right here. to make these signs flip-flops. Okay. So -1 to the n power times the R formula, you will get signs, R numbers of swapping sign, alternating signs, okay, as you go down the sequence. We call these alternating sequence. Sum. One of the big things we want to do is add the numbers all together. Okay, like for instance, the sales of merchandise, how much you throughout the month, each day, you want to add up the monthly total them. And to make it simple, we use a some Greek symbol, sigma, to sum. So if I read something as this, oh, sigma x, it means to add all the x. If you read, say, oh, on the papers, or you say, oh, sigma x times y, it means multiply the x times the y, then add them. Of course, if you see these, the x and the xy's, they will be explained clearly, should be explained clearly in the context on the page what the x's are and the y's are, in order for this command to make sense. Okay. We can even do better. Okay, we can use this notation to specify what we want to sum in the sequence. Okay, and here, if I want to sum the first 100 numbers, I will create these symbols for it. And how do I interpret this? Okay, first, the K is called an index. Okay, it's just like the Rolodex index card number 1, index card number 2, index card number 3. So it has, each card has a number on it. So you can say, I want what's on card number 10. You can pull it out. That's number, we call K, is called index. Okay. In these notations, you can call it J. You can give any symbols to create an index. K or N are used. Okay, so it says start on the bottom number and stop at the top number 100. Start 100. Start from 1, count to 100 of the cards, and pull out what the numbers are, F1 up to 100. Then finally add the sigma. Say after you get all these numbers lined up, sum them. That's the summation notation. So this one says starts from 4 to stop at 8. So 4, 5, 6, 8. 4, 5, 6, 8. 7, 8. You add those 5 numbers to it. The second one, well, 8, you add from the second entry up to the 5th entry. So the A sub 2 up to A sub 5, and add them all to the others. Everything in between. Okay, here's, you multiply the x and the y's from the 6th one, 7th one, pair them, 8th one, pair them, multiply, 9th one, pair them, multiply. After you got the 4 sets of multiplications products, you add those 4. And here's an abstract one. You start from some generic place, which we call n. And then you go and say, what do I stop? Well, you stop at n plus 3. That is 3 neighbors now. N plus 1, n plus 2, n plus 3. Then you stop them. Stop. Then you add them. And they're good for expressing formulas for involving sum. And here's a formula for mean in statistics. And so here's the way the formula is expressed. It's a lot shorter, easier to display than writing everything out, expanded form. Okay, so many formula statistics use a summation notation, and you have to be able to read what they are summing step by step. Okay. For instance, this, and I use the formula. The K actually gives the formula of the sequence. K start from 5 up to 8. You plug the 5 into the formula. Plug the 6 into the formula, and 7, and so on. You get 4 numbers. Then add. Okay, that's a command. Here, same thing. The only difference is you make sure you make the sign adjustment -1 to the k power. It's going to be minus the first one plus second one minus the second one, and then you combine them. Okay. This is called alternating sum with a sign flip-flopping. Okay. Well, these are the algebraic properties of the summation notation. Okay, if you're adding two sequences, you can break up, add the first sequence, then add a second sequence, add them together. Same thing for subtractions. Okay. It can pull a constant out. What it says is that, okay, and basically says if I have 5, if I have 5 times first number plus 5 times second number plus 5 times the third number, okay, these I can write as sum of 5 times 8i 1, 2, 3. It says, oh, you can take the 5 off. 1, 2, 3. In other way, you can just factor the 5 out, 1, 8 plus 1, 8, 2 plus 8. Okay. And that's what it says. What is not allowed is this. Absolutely no. Sum of sequence times 8 some dk. I got two sequences. I multiply them. Okay. And k could do 1, whatever to whatever. This is not going to be the same thing of adding them first individually, then multiply. Okay. This does not work in multiplication. You can pull out a constant multiple, yes. In general sequence, you may not do break up the sum of multiplications of sequence. But then what does this mean? If there's no k in the formula, it's a constant, that means you have the same number every time. So here you're adding up 5 threes is 15. Okay, here is basically, it shows you where these rules came from. Okay. We're going to sum one pattern, okay, and it's the sum consecutive integers 1 up to number n. Okay, and there's a trick. This is a famous trick for summing, actually for summing a linear formula. This trick will work. Okay, we're doing this just for this particular one. Okay, we want to sum 1 up to n, and what we do is we take 2 copies of it, write one of them backward, and actually instead of summing 1 copies, I sum 2 copies. Actually, that's easier to sum. You will see why. Because now notice if I add up and down each place, the 2 sum is n plus 1. Okay, and there are n sets of these, so the sum of 2 copies is n times n plus 1. So sum of 1 copy divided by 2 is n times n plus 1 divided by 2. Okay. And this is a sum of natural number 1 up to n. This is an important formula. Okay. So for instance, if I want to sum 1 to 100, it's going to be, n's 100. So it's going to be 100 times 101 times 2 divided by 2, 50, 50. Okay. I can use the trick to sum any linear sum. For example, if I plug in the numbers, putting 1, let's take a look at what the sequence is talking about. If I put x k equal to 1, let me set calculate k equal to 1, 2, 3. Let me calculate a few terms. When k is 1, this is minus 5. When k is 2, 2, 4 is minus 1. K is 3 is plus 1. K is 4 is plus 3. K is and then plus 5 plus 7. Yes. How many terms? They say, oh, I don't know, ask 45 of them. Okay. Right, that's 45. Okay, how do we sum these? Well, we can use the purpose of this exercise, use the rules we just abstract rules in the formula to get to the answer. First, I can break the sums up, okay, individually. And the sum of the 5s And the 2, multiple 2 can be pulled out as a constant, okay? The sum of the 5 means 5 sets of 42, 45. So this part is easy to figure out. Okay, and the 2 is outside. Now, what's the sum of these? These, the sum 1 plus 2 plus 3 up to 45. This is where the linear formula comes from. Okay, so then that we can get the answer. Okay, I will leave you to read the example F of shifting the, in case you don't start with k between 1, you can shift the formula a little bit so you can use the formula starting with 1 and so on. So, okay, and that's it. And do the homeworks on these. And yeah, have a good day. Bye-bye. Stop sharing.